Great. So yeah, I hope you all are able to see my screen. But yeah, again, welcome to our deep dive into modern recommendation system. The title of this tutorial is Unlocking Personalization. And in this tutorial, we'll explore how AI systems help match users with relevant content. And we'll go and do a deep dive into some of the modern recommendation algorithms. We'll cover both theoretical foundation and practical implementation of some of the recommendation algorithms. And I hope that by the end of the tutorial, you are able to have a better idea about how recommendation system work. And if you want to build those, you can do that for your company or as part of your side project. So I think I'm sharing the wrong screen. Let me share the right screen. Okay. There we go. Okay. So my name is Sarang, and I am a lead data scientist at a collaborative work management tool called Asana. I am based out of Vancouver, and today I'll be your tutor. So this is the table of contents. So the presentation and the tutorial is split into two parts. There is the motivation section where we'll talk about a couple of hypotheses and a couple of studies that relate to recommendation system, and in particular, why are recommendation systems important and why are we even here? And then the second part is the tutorial where I'll cover a bunch of different methodologies. We'll start with the input data. So looking at what are the different types of input data that go into recommendation system. We'll then talk about heuristics, how you can use business logic to power really simple recommendations. We'll then talk about three methodologies, content-based, collaborative filtering, and hybrid recommendation. And the tutorial is structured in such a way that we'll start with basic recommendations, and gradually we'll move on to developing something more and more complicated. And hybrid recommendations use deep learning and neural nets. So I hope you're still with me at that point in the tutorial. Great. So let's talk about the motivation for this tutorial. Um, so recommendation systems are ubiquitous. They are everywhere in our daily lives. So some of the key examples are listed here. So if you go on Amazon to shop for things or any other e-commerce website, you would see a page, something similar to this here, that shows your recommended items. Or if you purchase something, it'll show you items similar to what you've already purchased. If you watch TV shows and movies, this is a screenshot from Netflix, and it recommends your top picks based on your past history. It also recommends things like, because you've watched something, what are some of the things that you might like. LinkedIn, I use it for jobs and career search. So essentially, if you're looking for jobs, it'll suggest you your top job picks based on your profile, based on what you've interacted with in the past. Spotify, it has a made for you section. So it curates a daily playlist based on your listening history, and it profiles your taste in music and so on. Airbnb shows you some recommended vacation rentals based on your past stays and preferences. And finally, if you are on online dating, even Tinder has a recommendation system which matches you to relevant profiles based on things that you mentioned in your profile or your past swipe history. So again, each platform uses different approach to personalized content. We'll go into some of the approaches in today's tutorial and presentation. And in general, recommendation systems are, again, a very important part of our daily life. They shape how we discover new content and make choices. So I think it's very important to understand how they work, especially if you are a data scientist and machine learning engineer. Great. So what is a recommendation system? The definition is simple. It's a type of information filtering system that is designed to predict or suggest items or content that a user is likely to be interested in, or or generally prefers, or is likely to interact with on a given platform. The whole recommendation system can be broken down into three important components. So there's a component for the data, the input data, or the user preferences. Again, it can be explicit or implicit. We'll talk a bit more about this in the tutorial, But explicit data is when a user gives direct user input like ratings, reviews, and likes. Implicit is when we use like, users observed behavior like clicks, viewing time, watching history, and so on. Okay, so again, brings us back to the question, why do we need recommendation system? And I think the audience of this tutorial, because you all are here, I guess you already realize the importance of recommendation systems in our daily lives in terms of how we make purchases and make decisions. But I want to bring forth this idea through two interesting hypotheses and two interesting studies that were like, conducted and how they relate to recommendation system. So the way, number one, is something called the long tail. So essentially the way that we shop has changed over the past decade, past 2 decades, and so on. There used to be traditional stores, the traditional brick and mortar stores, where you used to go to purchase DVDs or books and so on. And they could hold only limited inventory because the shelf space was limited. They could only hold so much inventory. And also, they could only hold mainstream products. So basically, only the products that are really, really popular, that are profitable, they would hold that. But products that cater to like a specific interest or specific group of audience, those were tend to not like included in the shelf because they were not super profitable. They catered to a small audience, and again, there was limited shelf life. We've moved from those brick and mortar concept to the concept of online distribution. So with online distribution, online platforms, there's technically unlimited inventory. There's not a limit of how many movies or books can a website hold. And this gives the website the ability to essentially, this gives the website the ability to essentially like, offer niche products to like, to the customers and so on. And recommendation systems essentially helps users navigate this vast array of choices because, again, the inventories become unlimited. There are niche products that like, a company can hold on, so on. Great. So, uh, so let's talk about the long tail concept. So this brings us to the long tail concept. So if you look at this chart, which plots like items over popularity, there is the head. So essentially these are items which are like really high impact, popular. They are fewer in numbers, but they're mainstream. So these are the things that traditional brick and mortar stores um, were likely to like hold. Um, and then there's these long tail items, which are low impact, niche, many in number, and obscure. And given we now have transitioned from a brick and mortar, like, way of distributing things to online way of distributing things, recommendation systems make these long tail item discoverable. And they help users to find things that they won't discover through traditional browsing. So if we just show like, really popular items, they would not discover these niche items, which again, for a business can generate significant amount of revenue. And this creates opportunities for both consumers and content creators. So for consumers, they're able to discover things that they like. Content creators, they're able to cater and make really these niche products that might be targeted to a particular segment of customers. Great. So that was the first study. The second study that's really interesting and relates to recommendation system is the tasting booth experiment. And the setup of this experiment was basically, so this was an experiment that was conducted by two Stanford researchers, Iyengar and Lepper, and they set out to investigate the effect of choice on customer behavior. So for the setup of this experiment took place in a gourmet grocery store, so an upscale grocery store near Stanford University in the campus in California. And the setup of this experiment was that they set up two booths, booth one and booth two. Booth one contained 24 varieties of jams, and booth two contained like 6 varieties of jams, basically. And they wanted to test the impact of the choice quantity on customer behavior. So how does how does the impact, how does like the number of choices that a customer has available to them impact like customer behavior? So they try to control all the other factors. So they placed the booth strategically so that it has like similar foot traffic and other things like that. The only thing that was different between the booth was the number of samples that they had. And the findings for the study was really interesting. So about 60% of shoppers in booth one, actually like 60% of shoppers stopped at booth one. Whereas if you look at booth two, which held like fewer number of samples, only 40% of shoppers stopped at booth two. So there was a lot more foot traffic on booth one. But if you drill a bit deeper and look at like the subsequent purchases, uh, in tasting booth one, there was only 3% of consumers of those 60% consumers that made a purchase. But in booth two, even though it's a much smaller foot traffic, 30% of those consumers made a purchase. So the key insight from this was too many choices can paralyze decision making among customers. And this is really well depicted by this chart on the left, which shows happiness of the customers plotted against choices. So the happiness of or customer satisfaction increases until certain points. So until certain number of choices are given to the customer, they are satisfied and happy. But if you give them or overwhelm them with like too many choices, the customer satisfaction and happiness decreases, and it is stressful for the customer. And this is where recommendation system come into play, given with online distribution, there are a lot more choices. Recommendation system can improve customer satisfaction. They can increase conversion rates by simplifying decision making and by recommending only a limited curated set of products to the user. It helps eliminate this paradox of choice. So helping hopefully drive these many choices where the customer satisfaction is really low. So great. So we've talked about why recommendation systems are important from perspective of the long tail theory and the tasting booth experiment. So before we jump into some of the theory for our tutorial, I want to mention a brief history of recommendation systems. So the history of recommendation system traces back to late 1970s, and it has significantly evolved over the decades into a key technology that is now used by a variety of industries across different sectors. So the first known recommendation systems, the early beginnings, were actually developed in late 1970s by a scientist called Elaine Rich at UT Austin, University of Texas, Austin. And she developed a system that was called Grundy. And what Grundy was it was a computer-based librarian which was designed to recommend books to like the students based on their user preferences. So Grundy was a really simple recommendation system. What it did was it worked by asking users questions and classifying them into certain stereotypes based on their responses. And the system then recommended books that matched the preferences of the users, or based on what they had filled in a survey, it classified them into like certain categories and gave the same recommendations to all the users within a category. Um, in early 1990s was when the collaborative filtering approach became really popular. So this was uh, an approach that was developed by Xerox, and it's again in today's world, it's a widely used approach. Xerox developed this approach for one of the products that they were launching, and it was called like Tapestry, which was a document management system. And Tapestry introduced collaborative filtering and allowed users to manually rate documents, share their opinions with others on things that they received in their inbox. And this method or Tapestry basically laid the foundations for future automated recommendations algorithm. It brought collaborative filtering into picture, which is still a very widely used recommendation system algorithm. In late 1990s, Amazon started using collaborative filtering for product recommendations. And what their system did was it analyzed user behavior and preferences to suggest items that other similar users purchased. And it was hugely successful for Amazon. And their success in increasing sales through personalized recommendation, it spurred widespread adoption for recommendation system, particularly in e-commerce. Oops. Um, in in 2000s, Netflix started using recommendation system. Again, Netflix is one of the pioneers of recommendation system. You would often hear a lot of cool technology that Netflix ships in terms of the way that they recommend movies to their users. But they launched a famous contest called the Netflix Prize in 2006. And the prize was that whichever team or whichever research group is able to improve their recommendation system or recommendation algorithm by 10%, they would receive a prize of $1 million, which was great back at that time. And the winning solution pioneered hybrid recommendation. So it used an ensemble of 107 different recommendation algorithms. And it demonstrated the blending of multiple approaches and how multiple approaches, when applied together, can enhance recommendation accuracy. And now we are here, 2010 and beyond. Recommendation system have become a ubiquitous part of our daily lives. We see them on YouTube, Spotify, Facebook, a lot of different online platforms that we interact with. There have been a lot of advances in recommendation system, particularly with the advent of deep learning and deep learning becoming mainstream, and they become an integral part of our lives. So this is a brief history as to how recommendation systems evolved across the years and how they've become an integral part of how we consume content online and even offline. So let's jump into the tutorial now. Enough of theory. And in this tutorial, we'll cover 4 important aspects of recommendation systems. So we'll start with a heuristic-based approach, which uses predefined rules and business logic to make straightforward recommendation. Then we'll jump into content-based recommendation. So it recommends basically items to what users have previously liked by analyzing features of other items and then recommending what items are similar to the items that a user has interacted with. We'll then go into collaborative filtering, which is again a very, very widely used approach and a very popular approach, which suggests item based on preferences of users with similar taste patterns and behavior. And lastly, we'll go into hybrid recommendation system, which combines multiple recommendations approaches together and leverages the strength of each of the method. And this is a deep learning approach. This is complicated. So again, we'll go into this and hopefully you're still with me at that point of time. As we're talking through these different approaches, I have structured the tutorial in such a way that we start with something that is simple, so heuristic based, and gradually we'll look into more and more complicated approach. So to get you warmed up as we look at more complicated and more sophisticated approaches of recommending items to users. So let's talk about the input data. I briefly mentioned this in one of the previous slides, but there are 2 main types of input data. There is the explicit data and there is the implicit data. So explicit data is data where some sort of rating is given by the user. So not rating, but in general, it's basically a direct user feedback. So in case of, let's say, Netflix is developing a recommendation system, it has thumbs up, thumbs down. Users can rate movies 1 to 5. They can give reviews. Similarly, on Amazon, a user can rate the product from 1 to 5. They can give reviews and things like that. So this is direct user feedback. It is really, really high quality data because a user has given their feedback or their preference for the item. This data is hard to come by, so it's difficult to gather this data. This data might not always be available. as users might not spend time to rate items, or they might not even be applicable to the recommendation system that you're developing. The other type of data that we have is called the implicit data. And the data that this data is basically the behavioral data that we gather from users interaction with a given product, with a given website, and things like that. User do not give any specific ratings, but essentially we look at specific actions that a user performs on a given platform. So let's say we are building a recommendation system for Spotify. It looks at how many times a user has played the song. If you're building a recommendation system, let's say for Netflix, it might look at what movies you click at, which movies you navigate to. If you're building a recommendation system for Amazon or other e-commerce website, we might look at what items a user clicks or adds to their cart, and so on. Implicit data is a lot more abundant than explicit data, because technically you don't require the user to give a direct feedback. You are looking at their direct interaction with their website, but it's also a lot more noisier than the explicit data, and it might not directly express a user's preference. And there is a lot more data cleaning and wrangling someone that needs to do in order to use that in the recommendation system. Great. So we've talked about our input data. Let's talk about the different methodologies that we'll cover in our tutorial. So I'll start with some basic theory on each of them. And I think this would help you to understand the code more better as we look into the tutorial and as we go through the code. So heuristic-based recommendations are the simplest form of recommendations. They use predefined rules and business logic to make straightforward recommendations based on behavior and patterns. And again, there can be different heuristics that you might use for recommendation systems, and those depend on your business logic and on your product. Some of the common heuristic-based recommendations include recency-based or popularity-based. So for example, popularity-based recommendations recommends the most popular items to users. IMDb, for example, has something called IMDb's top 250 movies. This is also a very naive or simplistic recommendation system, which basically is a popularity-based recommendation system. So it ranks movies based on how popular they are and so on. Heuristic-based recommendation systems are really simple to set up. So that's a big pro. They only require metrics like sales or views, and it makes it really, really quick to deploy them. They also do not suffer from cold start problems. So let's say if a user is joining your platform, you do not need to gather any data about the user. You can directly recommend them the most popular movies or most popular products based on other users' interaction. So it does not suffer from a cold start problem. But the cons are pretty obvious. It lacks personalization. So essentially, it does not reflect individual users' performance. You're giving generic recommendations to everyone. So that's a pretty common cons. This is again a very simplistic way to recommend things, but it is still used across a bunch of different products, specifically for solving cold start problem when you don't have data for your user. So I want to talk a bit more about the popularity-based recommendations in terms of how the number of reviews are accounted for. So let's say you have 3 items. Let's say you're developing an online e-commerce recommendation system. You have 3 items. Users have rated these 3 items. There's item A, which has a rating of 5-star, but it has only received 10 reviews. There's item B, which has a rating of 100, which has a rating of 4.8, but it has only received 100 reviews. And then there's item C, which has the lowest rating among these 3, but it has received 1,000 reviews, so a lot more compared to item A and B. So the question here is, can we just simply rank these items based on their rating? So should we rank item A above item B and C because it has a rating of 5.0, much higher than item B and C, but it only has 10 reviews? And the answer is no. Generally, we want to see the item have at least certain number of ratings before we can have them on the top. And there's a very popular approach that is used to do this, and this approach is called Bayesian average. IMDb 250 list that we actually saw in the previous slide actually does this. So what it does is it is a Bayesian approach. So it develops a prior, which is C, and it's essentially the average number of ratings that all your items receive from all your users across all your data sets. So it's essentially used to set a prior, and then you have minimum number of ratings that are required. So again, you use this to set your prior. And then finally, you have your mean rating for the item that you're interested in calculating the Bayesian average for, and the number of rating for that item. And what this formula for Bayesian average does is it takes a weighted average for your prior and your item, and the rating for your item eventually gets pulled towards the average rating in your data set if there are very few ratings for that. So if, let's say, for item 10, there are very few ratings, what it would do is it would eventually get pulled towards what the mean of all your ratings in the data set is. So if we apply Bayesian average, we'll see that the item A is pushed to the bottom of the list in terms of recommendations for popularity, and item B and C are boosted up there. And this makes a lot more sense because, again, we do not want to recommend an item that's just rated like, 1 time or like 10 times, because a user that's generated that content might themselves rate the item. So very small number of ratings are not that reliable. So as you're developing popularity-based recommendation system, you would want to apply this technique of Bayesian average, again, used very widely across the industry. For example, the IMDb 250. Great. So the next type of recommendation system that we'll talk about is the content-based filtering. Again, it's a step above the popularity-based recommendation system. It takes into account user preferences. And what it does is it uses item features to recommend items that are similar to the item that a user has liked. And it looks at particularly explicit feedback, and it tries to look at the features and characteristics of the items that a user has already liked. So let's take an example for a movie recommendation system. Let's say we had a bunch of different movies, Shrek, Harry Potter, Dark Knight Rises, Memento, and Triplets, and we can place them on two axes. So one of the axes is the genre, so whether it's a children movie or it's an adult movie, and then we have another axis, whether it was a blockbuster or a mainstream movie. And we can place these place the movies on this two-dimensional space. We know about what these movies are. We know their plot. We know their ratings and so on. So we can place these movies. What we do then is, let's say if a user has watched Shrek and given that movie a rating of 5-star, we would recommend Harry Potter to them because this movie is similar to Harry Potter is similar to Shrek. It's a children movie. It was a blockbuster and so on. So this is a simple content-based filtering system. It places items on n-dimensional space based on certain features. And if a user has a high interaction with one item, it recommends items that are similar or nearest to that particular item. Major limitation for this approach, feature representations need to be hard engineered. So you need to know what features you want to encode for a given item. So you need to know these different features. For example, in this movie recommendation system, you need to know whether the movie is a blockbuster movie or it's a children or an adult movie. And it can only make recommendations, the system can only make recommendations based on existing interest of the users. So it does not include that component of serendipity. So it's not able to expand a user's taste, because what it does is it just looks at the movie that our users watched and it just recommends simple movies that are closer to the user based on certain characteristics and so on and so forth. So again, very simple recommendation system, just looks at user preferences and recommends items that are similar to the user preference. And you would have seen this in a lot of systems. This is again widely used. For example, if you see on Amazon, it has a section that says people who've bought this have also bought this. So it's basically based on like, content-based filtering, um, where it like, tends to analyze the features and characteristics of a given product that a user interacts with. Great. The next approach, again, the most popular approach, I guess I would say in today's recommendation system, is the collaborative filtering approach. And it uses basically similarities between users and items simultaneously to provide recommendations. The key component of collaborative filtering is a matrix which looks like this. It's also called the user and item matrix. And what it does is it essentially, the input data to this approach is this matrix where we have users as our x-axis and the items or movies, if you're developing a movie recommendation system, as the y-axis. And the values in this matrix are the interaction or the preference of a user with a given item. So over here, if you're developing a movie recommendation system based on explicit feedback, the values in this matrix are the stars that a given user gives to a given movie. So let's say user one rated these 3 movies. And this matrix is very sparse because generally you tend to have a lot of movies or a lot of items in your catalog and a lot of users, but users in general tend to interact with a very limited set of items. So it's a very, very sparse matrix. When I say sparse, it's basically a lot of values in this matrix are empty. So what collaborative filtering does is basically it looks at interactions of a given user, and then it tries to recommend item to a given user based on interest of another user that the model or the approach thinks is similar to a given user. So let's say, let's look at user one and user n. So we see that user one and user n have given a very high rating to this movie called Shrek. They've given a very low rating to this movie called Memento. So what the model does is it figures out that user n and user one are similar to each other. And because user one has watched or given a very high rating to Harry Potter, it would give the same, it would recommend Harry Potter to user n because it thinks that user n and user one are similar to each other based on how they've interacted with like, different products. So one of the big advantages of collaborative filtering is that like embeddings can be learned automatically. So as compared to content-based approaches, you do not need to rely on hand-engineered features. So you do not need to know particular features about your users and about the movies. So you do not need to know whether Shrek and Harry Potter are children movie or adult movies, whether they're a blockbuster or okay movies. The collaborative filtering approach basically automatically figures those latent features or those features out based on users' interaction with the movie. And basically, it can capture these complex patterns and relationships by learning these features automatically based on how users interact with different movies. So how collaborative filtering works? Again, collaborative filtering uses something called matrix factorization, which decomposes this user item matrix. Again, like it's the user item matrix that we looked at in the previous slide, into 2 matrices, which are user cross-latent features and movie cross-latent features. And there are multiple approaches to factorize a given matrix. There is the SVD, singular value decomposition, there's non-negative matrix factorization, and so on. We'll cover one of the approaches in our tutorial, but there are multiple approaches. And it decomposes that matrix into 2 matrix that capture these hidden patterns or these latent features. So basically, again, you are able to figure out certain features or certain characteristics of users and your items, but you do not need to like, hand engineer them, or you do not need to know these particular latent features, because what this approach does is it automatically filters these latent features out based on how users interact with items in your catalog. And this matrix factorization is the key component of collaborative filtering. Once you have user cross-latent features or you have movies cross-latent features, you can do a bunch of things. You can calculate what movies are similar to a given movie. You can figure out what users are similar to a given user, and so on. So it's able to capture these hidden patterns without actually us specifying or hand coding these specific features for a given movie or a given user. So really, really cool approach, really simple. And again, we'll talk about this in our tutorial a bit more. Cool. So the last approach that we'll talk about is the hybrid recommenders. And in particular, we'll talk about one particular type of hybrid recommender, which is called two-tower neural networks. And it's one of the most popular form of hybrid recommenders. And what it does is it combines the goodness of all the different approaches that we've talked together. So one of the drawbacks of collaborative filtering is that we specify user item engagement, but we are not able to specify item characteristics and user characteristics. So let's say like we have really, really good features or really good item characteristics that we want to input in our model. We can do that for collaborative in content-based content-based approaches, but we cannot do that in collaborative filtering. But at the same time, we want to include users' interaction with the items and like other similar users and things like that. We can do that in collaborative filtering, but we cannot do that in content-based filtering. Hybrid recommenders, two-tower neural nets helps us do best of both worlds. So essentially in hybrid recommenders, there are two towers, as the name suggests. There is the query tower, or also called the user tower. And then there's also the candidate tower, also called the item tower. Within these towers, you can feed in your user features and item features. There are neural nets. Basically, you can design neural net architecture based on like however you want to design it. And as we train the model, it eventually generates user embeddings, and we then can take a dot product of these embeddings and generate a similarity score, which essentially tells how likely a user is to interact with a given item, or basically a user preference. And our source of truth, again, this is a supervised learning approach. Our source of truth is a given user's interaction with a given product. But at the same time, we can also incorporate the user characteristics and the characteristics of our items through these neural networks or through these separate towers. So again, very, very powerful approach. This is also used very widely in recommendation systems that require that have a lot of user data or item data or item metadata or user metadata that could be really useful in informing recommendations. Great. Okay, so that's enough of theory. Let's jump into our tutorial. So in this tutorial, we will particularly talk about the movie lens dataset. We'll try out these different approaches on the movie lens dataset. Basically, movie lens dataset is the Titanic dataset of recommendation systems. If you've played around with Titanic dataset, it is the standard dataset that's used to teach machine learning, classification algorithms, and so on. And similarly, movie lens dataset is this Titanic or very standard industry dataset for recommendation system. Movie lens dataset was developed for research purposes. It's non-commercial, developed at University of Minnesota. And there are different versions of the movie lens dataset based on number of values that are, or based on number of ratings or number of rows that are available. So we'll particularly look at the movie lens dataset that has like 1 million rating. Again, 10 and 20 million rating datasets would require more compute, and then 100K I felt was like too small of a data set for us to experiment these different methodologies, particularly neural nets. So we'll be looking at this data set. You can access this through this link that's mentioned here at the bottom. Sorry. Yeah. You can access this data set through this link mentioned here at the bottom. And if I click on this link, it takes me to here, to this page, which is the page for movie lens. There are different data sets available based on how I um, mentioned like the types of data set on the previous slide. In particular, we'll be looking at this data set. So if you want to download that, you can download that. So this data set has about 1 million ratings from 600 users and 400 movies. It was released in 2003, so it's still outdated. It has movies that are like, quite old, but it's really, really good for learning and educational purposes. So if you could download this, just download this zip file. For this tutorial, we would also, all the material is available at this GitHub link. So if you click on this link, it will direct you to a GitHub. It's a public repository, which looks like this. And you essentially can follow through all the notebooks that we'll go through right now in this here. There's also the data set. So if you don't want to download it directly from the MovieLens website, you can essentially download this from this GitHub page. I recommend that you download these CSV files. The .dat files contain certain pre-process data that's like not processed yet. So I processed that data. You can find that in the CSV file. Great. So that brings us to the start of our tutorial. And before I jump into it, I want to see if there are any things on any questions so far. Great. Okay. So can you share the link? Yes. So let me send the link on the chat. This is the chat. This is the link to the GitHub. Great. Any other questions besides question from Mate? Oh, cool. So there's a question from Bilal that says, is there any recommended system which does synchronicity? I'm not totally sure what you mean by synchronicity here. Um, Bilal, would you clarify that? Okay, so if I'm understanding the question correctly, synchronicity probably means that it's able to use both content-based features as well as like user engagement. There is, we talked about like the two-tower neural networks that um, that does that. Okay, so the simultaneous occurrence of events which appear significantly. Okay, so Bilal says that synchronicity means the simultaneous occurrence of events which appear significantly related but have no discernible causal connection. Yeah, that's a good point, Bilal. So hopefully, two-tower neural networks are able to do it. So let's say in collaborative filtering, a user ended up rating two movies that appear to be related to each other, but maybe it's an anomaly because two-tower neural networks are really, really powerful. They encode a bunch of other features. Hopefully they help deal with that problem as well. So hopefully that answers your question. Not sure, but yeah, feel free to ask a follow-up question if it does not. Okay, how about serendipity? Yeah, great point. So serendipity. So for folks who do not know what serendipity is, serendipity basically means that sometimes like in recommendation systems tend to focus on particularly on things like that user have previously interacted with. So let's say if I watch a lot of movies that relate to thriller, action, and so on and so forth, I would be recommended a lot of movies that are like, very similar to like very, very like, thriller, action oriented and so on. Um, and if it is oftentimes it is oftentimes like, useful to give users the ability to like, explore new content. So like, broaden their taste, because sometimes user might like things that they've not previously interacted with, or things that are like not similar to the taste that they have indicated through their previous interactions and so on. So yeah, we include serendipity in recommendation systems. One of the ways to include serendipity is basically you can do like something hacky or something heuristic based, which is basically you can try to infuse some things that are like, really, really popular into recommendations um, of a given user based on their previous interaction. So let's say like, again, if I interact with thriller or action based movies, and we want to introduce that component of serendipity, what we could do is we could give like, top, like let's say top 3 movies that are like, not like thriller or action based. So let's say like, I'm recommended a movie that is comedy, but it's like really, really highly rated. And then we look at like a user's interaction with that particular new component. And if a user gives that like, gives that like comedy movie a very, very high rating, this would be incorporated in our recommendation system because they've rated that really, really high. And hopefully in the next iterations of like the recommendations that they're presented, those movies related to comedy are shown. And if a user did not like it, that would eventually be eliminated in it. Okay, so great. There's another question from Bilal. I did my master's thesis based on POI recommended systems, which use serendipity. My result was good based on only serendipity, not with novel. Also, I used only those users which have data existed, but not for the new users. It was a statistical algorithm, not AI. How to do it for those users which are new? So I guess like your questions around how to use serendipity for users which are new. Um, okay, so serendipity for users which are new, I guess like again, I think it would be like really, really interesting to look at your master thesis. But I think like from my understanding and from my experience working in industry, like I think for new users, what we generally try to do is um, we give things that are popular, but again, like, your popularity you can like tweak your popularity based recommendations in like, certain fashion. So you can like try to include recommendations. You can try to like segment your recommendations, your popular recommendations. So instead of going through all your popular recommendations that might be like, thriller based in terms of a movie recommendation system, you can give like, popular recommendations from different genres and see what users interact with, right? There's obviously a bias component here where like you would see that recommendations or like, movies that are up there on the top, they are interacted with more. But as your user gets accustomed to your platform, they tend to become like, your existing users. So you can eventually use the same phenomena that you used with your existing users to introduce that component of serendipity. So if a user tends to interact a lot more with comedy movies, but you think you want to introduce like, thriller to a given user, you could like, try to sneak that into your recommendations for the user. So that's one of the ways to do it. There might be some things that are like, more scientific, but in my industry experience, that's like, one of the things that we've used previously, and that has tended to work really well in terms of like, figuring out what are the things that a user might be interested in. Great. Okay. So I want to jump into the tutorial now. Um, Yeah, great. So looks like the link was incorrect. Thanks for catching that, John Baptiste. Great. So yeah, the link's in the chat. Feel free to look at this link. Again, the way that this tutorial is structured is okay. So I'll quickly walk through what this repository looks like. basically, there's this data 1M, which essentially has the data that from this movie lens website. I suggest that you download the CSV files again because those are pre-processed. The DAT files are not pre-processed. So yeah, recommend downloading those. And there are a bunch of Python notebooks here. Um, all notebooks have two categories. So there's a notebook called _tut, and there are notebooks without the tut. In this tutorial, we'll go through the notebooks that have tut in the name. These are basically, I've created a version of the notebook that has some fill in the blanks. So I think that'll make things easier as we walk through it. But all the solutions are available. Oops, I realized that I'm not sharing my screen and I apologize for that. Okay, yeah, so this is what the repository looks like. So there are two versions here. The TUT version basically is the tutorial version, the one that we'll walk through here. It has some fill in the blanks, makes things easier. You can again, practice as you're learning through it. And the solutions are basically available on here. So the one without TUT, they're available here. So if you want to look at the solutions, you can directly look here. Great. So let's jump into it. And I want to start with, I'm going to start with the introduction and EDA notebook, and I will share my screen. Great. 1 second. Hold on. Let me just set my environment up. Okay. So okay, so the way that this tutorial is, let me add another cell here. Great. Okay. So the way that this tutorial is structured is it's broken down into 7 steps. We will actually, no, I'm wrong. It's not this one. Yeah, let's use this one. Okay. So it's broken down into 7 steps. I'm using the ._tut file. So again, recommend you to use the tut file. But basically, it's broken down into 7 steps. We'll start with loading the data and doing some exploratory analysis. We'll look at heuristics. So we'll look at popularity-based recommendations. We'll look at content-based filtering and collaborative filtering, the approaches that we talked about earlier. And then we'll go into deep learning. So in deep learning section itself, we'll cover some large language models. So how you can incorporate large language models in your recommendation systems and so on. So that will again be part of our deep learning tutorial itself. So this is the flow, and I have structured all the notebooks basically through this. So all the notebooks are essentially labeled through all the different steps that we'll be going through. Great. So we'll walk through the movie lens data set. Okay, so let's go into it. So first chapter, loading the data. So again, you would find all the data in the data folder, data-1M here. So I'm just loading the data. In the CSV files, the data is separated by tabs. So it's technically not a CSV, it's a TSV tab separated value. So you can just add the tab here, and let's run this and let it load the data. Cool, our data is loaded. Let's quickly print the first rows of our movies data set. So I'm gonna do movies.head. There are 3 data sets. There is the movies data set, which contains movie IDs, titles, and genres. So what the movie is, what is the type of the movie, animation, children, comedy, and so on and so forth. There is there's a user's data set. We'll look into it, but let's quickly investigate the movie's data set a bit more. So I'm gonna print the info for the movie data set. Great. So looks like we have a total of 3883 movies. Looks like there are no nulls, but basically there's a movie ID, there's a title, and then there's a genre in there. I want to investigate this data set. So what I'll do is I will build basically a word cloud. What word clouds are essentially it's basically like what we can do is we can look at like what are all the words in the title for movies, and that will give us a picture of like generally in the 1990s, which this data set is from 1990s 1980s, what were like the most common titles in the movie. So there's this code for generating a word cloud, but basically there's a library that I'm using. It's called the word cloud library. It has stop words in it. So basically, in order to remove words like the, is, and things like that, we generally remove those words from the titles. We pre-process the title a bit here, and then we can use our myplotlib library to quickly plot to plot our the title word cloud that we generate here. So I'm gonna print this, and then whoops, I also need to generate the title corpus here. It takes a few minutes to run, and there we go. This is our word cloud. So basically what it does is it sizes the word based on like how much it is being mentioned in the titles of the movie. So you would see like back in the late 90s, a lot of movies mentioned man, love, night, day, dead, and so on. So this is just like pretty cool as you're like doing exploratory analysis for your data set. We can also plot the genres. So in order to look at like, what were the genres or the categories of the movies, we can quickly look at what the counts were in the genre. So what I've done is I'm using pandas to split the genres. So if you look at our movies genres, they are actually segregated by this like pipe operator. So I'm going to like do a quick count of how many I've like split the genres by this pipe operator, and I'm gonna do a quick count of like how many genres are there. And then I use my standard Seaborn libraries to plot this out. So basically I plot the values on the x-axis, and then I plot the index. Basically, once you do genres.count, it generates like a panda series that basically that has like index as the genre and the values as the number of times that was mentioned. So cool. So this is the distribution of our movie genres. Looks like a lot of movies back in those days were drama. So we have about 1,600 movies that had a genre tag with drama. A lot of movies comedy and action and thriller, and very few movies that were like fantasy, western, animation, and so on. Pretty interesting. The second data set that we have is called users. So let's look at the users data set. Pretty standard. If I do ahead, it has user IDs. It has a bunch of information about our users. So like, the gender, age, bunch of like the demographic characteristics of our users. Let's do a users.info here. And it shows we have 6,040 users. And it also it shows that there's basically no nulls, which is pretty good. Great. Let's quickly plot. Maybe in the interest of time, I'm going to skip the plottings here, but you can take a look at the solution, which essentially shows the demographics plotted for our users. So basically, like we have a lot more males in our data set, what the age distribution is, what are like the top 10 occupations, and again, like the age distribution for different occupations. So this is really interesting. It's not directly applicable to like, things that we would be talking about next. So I'm going to skip that in the interest of time, but you can take a look at the solution notebook and it would show this basically. Great. Okay, so the third data set that I want to quickly talk about before we go into the methodologies is the rating data set. So I'm going to print ratings.head, and I see we're going to ignore these two columns for now, but basically I see for a given user and a given movie what is the rating and the timestamp for when they give the ratings. These are some noisy columns in the data set. So let's just drop them quickly. So just using my standard Python data set functions to drop these. Oh, yeah, sorry, there's already been dropped. So let's just do a ratings start head. Cool. So this is what our ratings data set looks like. Ratings, movie ID. So what is the rating that a given user is given a movie, and what is the timestamp for that? Let's do a quick ratings.info, and yep, looks like there are no nulls. Great. Let's also plot the distribution of ratings. So what I'm going to do is I'm just going to use my standard matplotlib library and then plot the distribution of ratings. So as you can see here, looks like the ratings are skewed towards 4 and 5, 3, 4, and 5. So users tend to give a lot higher ratings, but a lot lower ratings. So it looks like there's quite a bit of bias in our data set. But that's fine. Let's play around with this bias. But that's very common. Like, if you're looking at any recommendation system, or if you're looking at like, any ratings, you would see a lot of users tend to give ratings at the extremes, because generally whenever a user like super happy with the product, or like you super dissatisfied with the product, that is when they would like, tend to like rate a given product or something. If it's like average, they tend to like, ignore it and stuff like that. So that's like a very common problem across like, all the data sets that are in recommendation systems. Cool. So I'm also going to do a quick describe of the data set. So again, we have about 1 million ratings. That's the 1M data set that we're looking at. Minimum is 1. And whoops, for the rating. Sorry, so the minimum is 1. Looks like the 50th percentile is 4, which is very, very interesting. So again, our data set is kind of like skewed towards 3 and 4 and 5 ratings. So the 25th percentile is 3. But again, like I think this is all rounded up. I think the 50th percentile is about like 3.5-ish or something when I investigated it last. Cool. So I'm going to combine my data sets. Basically, I'm going to merge my movies and ratings data set, and I'm going to put them in data set combined. I've already, in the data 1M folder, there's already a data set combined, but I am just going to combine them because it's just like good to look at everything together. And that's like the main data set that we'll be looking at. Cool. So this notebook has a bunch of EDA. Again, sorry for rushing through it, but feel free to take a look at the solutions. It has like, I've also written some notes and things like that, that talk about like, the general EDA that can be done. Great. Okay, so let's jump into our second tutorial, where we'll talk about in this tutorial, 1 second, let me just open up my notes. Great. Okay. So in this tutorial, we'll quickly talk about popularity-based recommendations. Again, these are very simple, nothing so complicated. So this is a pretty short notebook. Basically, I'm going to import my standard library. So import pandas, import numpy as np. Oops, not no. Mapping to my kernel. Going to read my data using the read CSV function. This is the data set combined that I'm looking at. Basically, what it does is it combined users, movies, and ratings into one data frame. So for a given movie, we also have its description as well as the rating that different user has given, as well as the demographics for the user. Again, in popularity-based recommendation systems, basically what we do is we look at what movies are the most popular ones. So what I'm going to do is I'm going to group my data frame by the title and then look at the rating. What is the average number of, so I'm going to look at the median. So what is the median rating as well as how many users have given a rating. So I'm looking at both median and count, and then I'm going to sort my values by the median. So again, looking at this, looks like To Live, a 1994 movie, has the highest median, actually not the highest median, but a bunch of movies have a median of 51. But again, as I mentioned in the slides, we should not directly use popularity-based recommendation systems because we need to take into account how many times a given movie has been rated. So I use the Bayesian average, essentially. So this is what we talked about. Bayesian average basically establishes a prior. It looks at what is the global rating across all your movies. You can set up a minimum threshold here. So essentially, what is the minimum number of minimum number of ratings that you want to look at, and so on. So this is like a common formula that is used for calculating like a Bayesian average. So I've written down a function here. Basically, we calculate this. So we multiply C by C into M, where C is our global mean rating. So the global mean, I'm taking a median here. So I'm taking the median. And then I multiply that with the count. So here. And then to calculate what is the threshold that I want to apply on my minimum number of ratings, I can basically take a quantile. So basically, I'm looking at what is the quantile of the number of ratings that a user has provided on a given movie. So let's say if you have 5 movies and the quantile is 10 ratings, let's establish that as our minimum number of ratings that we require. So I'm just going to run this cell and then again sort the values by Bayesian average and then generate a head here. Great. So I see the ratings have completely changed from what I see here. I see American Beauty, a very, very popular classic movie, high up there, has a very high count, has a very high Bayesian average rating. Star Wars, Save It, Private Ryan, Matrix, Silence of the Lambs, very, very classic, very popular movies from the 90s, all being populated here. And if I look at this movie called Slav's Brooder, Brothers of Sleep, that has a count of 1. If I click on this, oh, I see it has a Bayesian average of 3. So this has been downgraded from 5 to 3 because, again, it has a very low count rating. Great. So this is our heuristic-based recommendation, very simplistic. But if you're using popularity-based heuristic recommendation, I encourage you to do a Bayesian average to account for the count of ratings. Awesome. Now let's jump into our next approach, and that is the content-based filtering. And before I jump into content-based filtering, let me take a look at the chat quickly to see if there are any questions. Looks like no. I think we are good to proceed. Let me go back and share my screen. And again, this might feel a bit rushed, and I apologize for that. I suggest that you look at these notebooks and the solutions. These are all provided on the GitHub link. All of them have really, really detailed descriptions and comments. So hopefully it helps you understand the code as I'm walking through it. Great. Okay. So let's look into our next, the content-based recommendations. So again, doing the standard stuff, loading my libraries, pandas, numpy, matplotlib, reading my data sets. So reading the ratings data sets, the users data sets, the movies data set, and the combined data set. Cool. All read in. And again, content-based recommenders. We talked about the theory a bit, but basically, if a user watches a given movie, we find similar movies based on genres, actors, directors, storyline, and so on, and then recommend those similar movies to those. So you need to hand code those features. Great. Okay. So there are multiple steps that one goes through for building a content-based recommender system. This is a flowchart here. Basically, we'll extract features of different items. So in our case, we don't have a lot of features because this is an educational data set, but we would mainly look at the genre of a movie. That's like one of the features that we have for our movie. So if we look at our movies data set, it has the only features that we have is genre. So we're gonna find movies similar to a given movie based on the genres that are encoded. And a given movie can have multiple genres. So that is an important information that we would use. So let's start with preprocessing our genres a bit. So again, genres are currently encoded in such a way that there is pipe operator between all of between all the genres that a movie is part of. So I'm going to split this up and then put this into an array. So I'm going to split my movie genre column. I'm going to split it by this pipe operator. And then I'm going to fill any. So there might be even though there might not be a null. In general, this data set does not have a null, but I'm just having this just in case there is just in case there's something, there's an anomaly or something. So I'm running this pre-processing code, and when I do that, I see that my genres are split into an array, and this array is indicative of what the genre a given movie title is encoded into. And for computing the features of a given movie, I'm going to use TF-IDF. Again, TF-IDF is a very popular industry-wide approach. Basically, what it does is, in our case, what it'll do is it'll basically look at it considers every movie as a separate document, and then it looks at what are the different encodings for every movie in terms of what are the genres. So let's say if a lot of movies in our data set have a genre of children's, it'll downweight children genre. And then if a movie is specifically has a specific genre of animation, and very few movies have animation as their only genre, it would weigh those movies together. So this is a way to essentially encode features for it's only used in natural language processing, but this is a methodology that we can use in our data set as well. So scikit-learn has a TF-IDF vectorizer. So I'm going to use a TF-IDF vectorizer here from scikit-learn. And I'm going to remove stop words, the English stop words here. And then I will just fit my data set on a TF-IDF vectorizer. So what it has done is it's for every movie in my data set, it has built 127 features. It has built 127 features because I've also used an n-gram. And n-gram basically looks at words that might be co-occurring together. So it has 127 features, which are basically genres of a given movie. And once I have this matrix, I essentially can calculate cosine similarity. Again, a bunch of different similarity metrics. Some of you might be aware with cosine's distance. Euclidean distance, Manhattan distance, and so on. So I'm going to use cosine distance for here. Again, scikit-learn has cosine similarity built in. So I'm going to use cosine similarity. Going to calculate cosine similarity of my TF-IDF matrix with itself. So if we look at our TF-IDF matrix, dot dense, too dense, I think. Oops, let's not have that attribute. Okay, so this is what our matrix looks like. So this has all the movies, and then all the movies are encoded based on their genre. It shows 0 because, again, there are 127 values in here, so some might be populated in between. But yeah, so I calculate cosine similarity. And then I have a function here that basically, given a movie title, it calculates the most similar movies to that given movie. So running this function, and I am going to calculate similar movies to this movie called Toy Story. So if you run this function directly and I run this, it gives me the similar movies to the movie Toy Story. And as you would see, I think this makes sense to me. Aladdin, again, a kid's movie, animated movie, American Tail, I haven't seen it, so I don't know what movies it is. Rugrats, Bug Lives, Toy Story 2, very similar to the movie here. So if we, using this methodology, using TF-IDF and calculating similarity scores, if we input a movie, we can eventually calculate what the similar movies are. Similar, if I look at the matrix, it gives me very similar movie to the matrix. So Nemesis, Nemesis is a movie that I've not seen. I've seen Terminator, but yeah, movies along the similar themes. Great. So once we have these things that we've generated, content-based recommendations, what basically you can do is, like, if a user's watched a movie, rated any movie 5-star, you can just recommend all similar movies to that based on these content-based recommendation systems. Great. So there is another way to calculate recommendations for a user using content-based. So one of the ways, as I mentioned before, was that you can technically just recommend the latest movie that a user has given 5-star to, and then you can surface all the similar movies to that. The other way to do it is something called using something called user profile creation. And what user profile creation does is that, we have these vectors, these TF-IDF vectors that we've created. Basically, for a given user, all the movies that a given user has rated highly, let's say 4 or 5, you can average those vectors together for a given user. So let's say I'm user 1, I've given movie 5 and 6 as a really, really high rating, rating of 4 and 5. I can average those vectors. I can take a simple mean or simple average of those vectors. So let's say I've given these two movies very high rating. I can just average them and then calculate similarity to those to that average vector. So calculate the similarity of the movie to that average vector. And this is good because instead of relying on just one movie, you are generating a user profile using the average of all the vectors. So, like, the user profile is like all the movies that they've rated highly, just averaging them. And then, this is basically depicting a given user's taste, because for every movie that a user's watched, we are taking that and, like, taking that as a component in this user profile. So the code here basically walks through it. I'm going to skip that again in the interest of time. But basically, it creates a user vector. It averages a user's profile based on the movies that they've watched. And then it calculates those similarities. So given for every movie in our data set, it calculates the movie similarity with the profile that we've created for a given user. And then simple standard functions for calculating recommendations for the movies. So again, solutions are here in the non-TUT version, and you can look at, like, once you create a profile, you can just enter any user ID and then it will output the list of movies that we should recommend to that given user. Great. Okay. So we have 5 minutes. I am going to talk about collaborative filtering quickly because this is where I think this is like the most popular approach, to be honest. Like in industry, I've used this the most, even over like neural networks. This is really, really simple, really intuitive. And that's why I want to spend like the next 5 minutes talking about like, collaborative filtering approach. Um, Great. So opening this notebook, 04 TOT collaborative filtering. Let's load a bunch of libraries, and I am going to just copy paste the things from my solution in the interest of time. Let's load the data sets. And I am going to do a quick head here. I have my combined data set. Okay, cool. So if you remember from the theory that we talked about, the key component of collaborative filtering is the user movies matrix. The values in this matrix are the ratings for the user. And basically, we need to generate this matrix from this data.